Awesome. Okay, I hope you guys are getting on fairly well. Hopefully by now you've at least loaded in your models and kind of figured out where to get with the Gaussian mixture model and loaded in your variables. So once you've done that, you can actually get stuck into the loss function. So first of all, Willie and a few other people online were kind of hoping I would go through a little bit more of the theory behind the loss function. I think it's a good idea before you get stuck in. So I'm going to load up the paper here. I will also try and zoom in so you can see it. So this is the VaDE paper, which I gave you the link to. And this is the equation. Equation 12 was the one I was showing you earlier. But people wanted me to kind of go back a little bit and give you some of the background behind it. I was actually sitting here for the last 20 minutes trying to figure this out myself. So if you want this to turn into a discussion, it can. And if you want to dive in deeper, I probably will need your help to go through that as well. But let's start off with the top here. So this is kind of, first of all, some pseudocode to get you through the initial part of the loss function. But a lot of this has been done already. You know, we've already got our initial variables. And I find this kind of hard to work with when you're translating it into code. So actually, I'm going to skip over that because it can be kind of confusing and come back to it later. So first of all, we're going to first look at, where are we going to look at first? We'll look at the first, like section 3.2 here, where they kind of define what exactly is the error within our VaDE function. So this is a log likelihood of VaDE, and it's a joint probability of x, which is our input, z, the latent space, which I mentioned, and c, which is the clustering, so the pi, mu, c, and log c we just set into our code. So that's kind of the three things that we need to essentially combine within this error function. So they also mentioned straight after that equation, we're going to estimate the z component and the cluster component, which are the two parameters we need to learn, given our data, with this term here, which is the joint probability of x, z, and the cluster, as well as this q, z, c, and x here. So first of all, the joint probability at the top here has been expanded in equation 3. So it's been expanded into 3 different terms here. And actually, you'll see that they break them down into 4, 5, and 6, and also further down. However, what I want to talk about first is the bottom part here, the Q, Z, C, the joint probability of Z and C given X. So for that, they've also broken it down. So they actually state in the paper, we're assuming this is a meaningful distribution and can be factorized into these 2 components here. So first of all, z given x, we've already seen that before with our VaDE. So how do we compute the latent space given our x? We know how to do that already. So that should be taken care of, or you should at least know how to do that given the loss function that we saw with the VaDE last week. This last part here, c given x, you actually need to scroll all the way down to this part here to get that particular part figured out. And actually, when I was implementing this loss function, I started off with this particular part here. And the reason why is because this pz given c, you need to kind of build a Gaussian, your Gaussian distributions. And if you remember from last week with our VaDE, the way we got those Gaussian distributions was by using a built-in function, I believe, which we could just sample from. I found that realistically when working with this, because you need a Gaussian distribution for each individual cluster, so you need to basically create a for loop, go through each cluster, and get a Gaussian distribution for each using that mean and variance you just learned with the Gaussian mixture model. I just found that I had to create my own Gaussian distribution function, which should be fairly simple. It's a one-liner, but I just found it easier to implement that myself. If you can find a way to reuse what you did last week and kind of build that into your for loop, you could possibly do that as well. But look at the sample code. The sample code that was provided in the original implementation, use that as a baseline. In fact, you could essentially copy and paste their Gaussian PDF function there and just transfer it into PyTorch code. So implement that Gaussian PDF first. and build this particular component of the loss function. That's where I would begin. It's a fairly simple, you know, I don't know, about 10 lines of code. It shouldn't take too long, but just to get your head wrapped around the sampling part for each individual cluster. So I'll give you a couple of minutes to do that. If you get ahead of that and you're able to get that Gaussian PDF function done, start your loss function, call that Gaussian PDF function for every cluster, then you can start plugging in the rest of the parameters. So this is, and also in the loss function, what you should be able to do really easily is the cross entropy part. So that's the part, I think I put a comment there as the first term, which is define the cross entropy, because that's just calling the function binary cross entropy, your reconstructed x, which I'm just found out that I had it up here already. So here is our loss function. Sorry, where did it go? Here. This is our loss function. This is a Gaussian PDF function that I was talking about. You'll find a similar one in the original implementation in TensorFlow. Just translate that to PyTorch. And in here, you're going to compute your cross entropy, which is done using a built-in PyTorch function, which will take recon x and compute some sort of cross entropy. So get that started, and we'll see how you get on with that and return in a few minutes. I will go back to the, sorry, was it a question?
No question, but I copy-pasted the solution for step 1.
Oh, perfect. So if you didn't hear that, the solution for step 1 has been copied and pasted. So the Gaussian mixture model part, where you set those, the pi, mu c, and log c, have all been uploaded into the document. So just refresh that and you should be able to see it. Correct. So that's the bottom part of this particular equation taken care of. So the top part is the part that I need to use my notes for. So we already said that it was factorized out. Where did I say it was factorized? Here. So we have the probability of x given z, which is given here. And that should be identical to how we did it before, because this is the mean x, variance x, which is from the latent space. So that's exactly what we had in our variation autoencoder. So n here is a Gaussian distribution, I believe, and Ber here just means a Bernoulli distribution. If you look in the pseudocode here, it just tells you there if it's binary, then use one. If not, use the other. We'll just assume to use the Gaussian one because we've been using Gaussian so far. I don't see any reason to complicate it, so feel free to use Gaussians here. This is a categorical distribution, all parameterized by our pi, mu c, and log c. And the probability is z given c is the same as our Gaussian distribution here, but instead of using the mean of the latent space, now you're going to switch to the mu c log c instead of the mu z log z. You're just going to switch that out for that, and it should work the same way. Or you can use your built-in, or you can reuse the code that you used last week for this part, and you use your Gaussian PDF function for that part, because you've got multiple clusters, so you need to do one for every single cluster. This C here is indexing the cluster, so remember to do it for every single one. That's it from me. I'm going to let you go ahead and create that Gaussian PDF function if you feel like you need it or not. It's up to you. I would highly recommend using it because the original code also uses it, and you're kind of using that as a template, so it'll just make more sense as you move forward. And yeah, we'll kind of give you the code progressively as we go along, but very rapidly because we're running out of time. Hope that answers some of the questions online about the paper itself. All right. Great. Okay, so you guys have had a little bit more time to get familiar with the loss function now. So we've updated the Colab file again. So I think this might be the last time we update it before we give you the final solution. So I've just filled in the Gaussian, oops, sorry, I lost it there. I just filled in the Gaussian PDF function there. Let's go back down, there we go. So I filled in this part here, and I also filled in the cross entropy part, the sampling as you would do in the VaDE, and calling the Gaussian function for each cluster to build this G matrix. And then this is the part in the paper, which was this part here. So this is this part kind of done and dusted, so you can go back up to the overall elbow function and kind of just fill in all the missing pieces now. So you've got QC given x, and I would advise you kind of go up to equation 9. Sorry, back to equation 12 actually, because you've kind of got most of this figured out now. So you've done your cross entropy part here, and you've kind of done a lot of the part in here as well now. So yeah, you're kind of just putting it all together now. There's a little bit extra that needs to be done to add this bit here and this bit here. And I think that's the majority of it. I can't remember exactly from my code. I'm just working from memory here. But the cross entropy, this part here is done. I'm fairly sure most of this is done now as well. And you can start working on incorporating pi and this part here. And then see if you can kind of plug it all in together. Yeah, if you have questions, your TAs are on hand. But there's just a few lines of code left, about 3 or 4 lines left in order to complete this loss function, and then you should be able to run it. We will upload all of the code by the end of today, so you can actually run it from start to finish. All right. Okay, welcome back, everyone. We're just wrapping up now. So all of the code has been updated on the Colab notebook. We're just double checking to make sure it's all looking all right. So there are a couple of things that came up on Slack, and I just kind of wanted to talk about it because a lot of people were discussing kind of the same thing. So it was, why do we use the Z encodings in the Gaussian mixture model? And really it comes down to, we've done a lot of the legwork to model the data in the latent space. So actually clustering from the raw data seems pointless when we've already done a lot of the legwork to kind of do our dimensionality reduction, model it in such a fashion that it replicates the data fairly accurately without the additional noise. So we've actually got a really good representation in the latent space, hence the reason for using that to create the clusters. It also reduces the amount of the number of parameters you need in order to create those clusters, because all we've done here is added 3 additional parameters within our VaDE model. Whereas if we were trying to do that all the way from the raw data up to those clusters, we'd probably need a lot more parameters to get there as well. So a lot of that is implementation, but a lot of it is intuition as well. You know, it just makes sense to use that latent space. And there was also a comment about why did we use Z-mean instead of sampling from Z-mean and the log variance as well, and then using those sampling terms. Honestly, I don't know the answer to that. I would assume that if you use both the mean and the variance, you'd get a nicer representation of the data. So if it was me, I would just go ahead and try it and see if that improves your performance. So we've uploaded the rest of the code, and you'll see what I mean now by just plugging the rest of the equation 12, I believe it was, which is here, into the rest of the loss function, because we literally just do exactly that. And I've lost my loss function again. Here we go. We literally plug in everything as it appears in equation 12 and add it all together, and that's our loss. So here's the cross entropy term, our 0.5 times this intercluster relationship, which I talked about in equation 12. So this part, this part here, plus the 2 additional terms at the end there, which I call PC1 and PC2. So literally plugging in the numbers and putting them all together. And this should run. This should give you something reasonable. Feel free to change the number of clusters. And also there's a test function provided right at the bottom here to take your to take your recons, your mu's from the clusters, the means and the variances from the clusters, and actually make a predicted cluster label. So that's all been provided there as well. You'll notice that it uses the Gaussian PDF function that we've used before, which is why it was outside the class, so we could kind of call it wherever we wanted it. And this should give us a cluster label, which you can then use. So here, all I did was print it out, so print clusters. I would not advise just printing the cluster labels. I advise you to take those cluster labels and use the evaluation metrics, which I mentioned in the lecture, and actually try and evaluate how well these models are working, and then boost up the number of classes, and then again evaluate how your models are working. Try some visualization techniques. There's a lot you can do with this model now that you have it up and running, and I would encourage you to go ahead and do that. So you'll notice that this particular session was quite technical compared to last week. There was certainly a lot more to learn and to pick up from the paper itself. I think a lot of it was actually figuring out what exactly the paper meant and translating it across to code form. We're actually thinking about what to do next week. So if you found this too technical, or you think you're happy to go at this level, please put that into the feedback forms, which I believe Amar just uploaded a link right now to. So you can put all your comments. It's on Slack, so you can put all your comments about how technical this particular session was, and we'll adapt and change for next week. And with that, I'll conclude this session. Thank you very much for joining us. We'll see you again next week.